about sieves. Let's do a crash course in sieving.
Because the sieves that are used in analytic number theory, they aren't very similar to Eratosthenes' sieve.
So let's get there. Let's get there. So what I want to prove for you is a theorem of Brun from 1919, just celebrated its 100th anniversary. Unlike Dirichlet, right? Dirichlet says sum over primes in progressions diverges, and therefore they're implementing primes in those progressions. Brun says you're not going to be able to prove twin primes that way. If you sum over twin primes, 1 over p, this converges.
Do we know to what it converges?
Oh, it depends on, I haven't been specific about what I mean by twin primes. Do I mean that a prime is a twin if it's p such that p plus 2 is also prime? Or do I mean all pairs p and p plus 2, which doesn't matter because that doubles the, so what the exact constant is depends on your definition. And people compute these things. I don't think it's anything, interesting.
But it's very unfortunate that this converges. Right?
It's somewhat unfortunate that it converges. On the other hand, it has to converge because that's what the theory says.
So why is it unfortunate? Is
because if it was infinite,
if it was
infinite twin primes,
if it was infinite,
right?
Yeah, if it was infinite and you could prove it, then
yeah, so then it's like, but then a lot of math gets developed to study these sort of
Sure.
objects,
Yeah.
right? And then
all right, so let's see how I want to actually prove a theorem. I always I want to break Zeno's paradox and get to the end and actually prove this theorem for you today. Right. So what he really proves, he didn't phrase it this way, but what we will prove is that pi 2 is a number of twin primes up to x, number of p up to x, so that p plus 2 is also prime, is bounded by x over log squared x, not x over log x, but x over, there's a 1 over log for p being a prime, there's another 1 over log for p plus 2 being a prime. So that's x over log squared, and that will immediately imply this by partial summation. Yeah. Should I show you the proof, or you see how to do it?
I'm just sort of parsing the asymptotic, I guess.
So what I'm saying is the number of twin primes up to x is bounded by x over log squared x. And so then if you want to know how many, yeah, so then this is the integral from whatever, some constant up to x of 1 over t d pi 2 of t. This is just the, still just integral. Okay, so if you integrate by parts, you get pi 2 of x over x, which goes to 0. There's a constant. And then an integral from 2 to x of pi 2 of t, and the derivative of 1 over t is 1 over t squared dt. And so this thing, by this theorem, is the integral up to x of 1 over, so this is t over log squared t, and this is a 1 over t squared. So I get a 1 over t log squared t dt.
Yeah, this change
And this is convergent.
Just barely, yeah.
Just barely convergent. Unlike the primes, where this is 1 over t log t, which is divergent, this is convergent. Okay, so it's enough to prove this.
So this is some sort of a, I guess if you do P2 of x over x, it's like the probability that we are on that set. And then you have P being a prime 1 over log x, and then P plus 2 being prime 1 over log x again. So some sort of a
Independence.
Independency of some.
Yes.
Yeah, like
and the truth is they're not independent. There's a local factor, and this is what the Hardy-Littlewood conjecture, K-tuple conjecture in general is that this has an asymptotic expansion, and that asymptotic formula is not 1 times x over log x, but some constant times x over log x, where that constant is measuring the local probability. So it's an adelic. It should really be an adelic thing.
Yeah, this is what I did, but I'm not. Okay.
In other words, this is just the prime at infinity.
So adelic, when you say adelic, you mean like p-adic in a sense?
P-adic at every p at every prime. The combination of all of them together. Yeah. But let's not go in. I want to keep this very elementary. So let's start with Eratosthenes. So here's one thing that we might want to consider. Let's look. So following Eratosthenes, Eratosthenes,
Eratosthenes, yes.
Eratosthenes. Following Eratosthenes, we will look at the following SXZ. This is the sum over all, let's say, numbers m up to x. And then the indicator that m times m plus 2 is co-prime with pz, where pz is the product over primes up to z of p. Let's parse this. Okay, so I want to know how many numbers there are up to x, so that if you take m times m plus 2, it has no prime factors in common with any of the primes up to z. Okay, let's say we can take z. Z is going to be a parameter, but let's say we can take z like...
They're both prime, right? Is what this is going to pick up.
That's exactly what it's going to pick up. And this was exactly Eratosthenes' key idea.
Yeah, that's true. Yeah.
If a number has no prime factors less than 100, and it's less than 100 squared, then it's prime. So if this number, whatever it is, has no prime factors less than x to the 1/3.
And x to the 1/3 is what's going to work out.
Yeah, then the only way for this number to be less than x to the 1, to have no prime factors less than x to the 1/3 means each of these has to individually be prime. Then this is catching twin primes. This catches twin primes. This catches twin primes. Okay, in other words, i.e. Pi 2 of x is bounded by, now it drops the first, if there are twin primes less than x to the 1/3, it drops them. Right? Because it's and then put an SXZ, where Z I'm thinking of as being in this range.
Wait, what do you mean by you dropped?
So I threw away, if I had twin primes less than x to the 1/3, they got thrown out because they have a factor in common with primes less than x to the 1/3.
Oh, you're saying
so the actual number
parameter PZ, right? Because it's Z.
Z, yes.
Oh, okay.
Right. So for this value of Z, we can bound the number of primes, number of twin primes up to x by x to the 1/3, which obviously is less than x over log squared x. So we don't care about this. We just need to bound this. Okay.
And so what Eratosthenes had done was he just stopped at this point.
Well, he didn't consider twin primes.
Right, he just did with regular numbers. What I mean is that he did this indicator function thing. He did the x to the 1/2 thing, and that was it. Right?
Yeah, and we can be a little generous and say, if you have a number of size x, and it has no prime factors less than x to the 1/100, the same idea that Eratosthenes used tells you that that number is at most a product of 100 primes. And in fact, that's what Brun also did, is he showed that the number of numbers n up to x, so that both n and n plus 2 have at most 10 prime factors, is at least x over log squared x.
Interesting.
So it's some almost prime, progress towards twin primes.
And why was this natural to think about? Like Eratosthenes was such a long time before this.
Yes.
What were like some precursor ideas?
We're going to get there. We're going to get there. The next idea is Legendre's idea. Okay, so we need to understand S of XZ. Again, it's this thing. Legendre, the Legendre sieve, Legendre idea is to get it by inclusion-exclusion, which some people attribute to Eratosthenes anyway. But Legendre's idea is inclusion-exclusion. Inclusion-exclusion, in what sense? Well, it's very simple. If you want the indicator function of something being 1, recall that if you have a function f and you convolve it with Mobius and you get a function g, that's true if and only if g convolved with 1 gives you back f. In other words, if you have an L series with f and you multiply it by 1 over zeta, and that gives you the L series with coefficient g. F and g, f, g, and Mobius and 1 are all functions from the naturals to the complexes, if you like.
And when you're multiplying and adding things in series, then that's what you're calling doing an exclusion.
That, yes, exactly. In particular, the sum over the divisors of n of Mobius of d, we already saw, is either 1 is the indicator function of n being 1.
Right.
Okay, which is an immediate consequence of this with the function g being 1.
Mobius's inverse is 1. Right?
Yes, or f rather being 1, and g being f being zeta, which is all 1s, and g being the function 1.
Yeah.
Right. This is just saying that zeta times 1 over zeta is 1.
It's kind of funny that the function that's always 1 is not the identity function in this group.
That's right, because it's always 1. Yeah. So let's stick that into S. So S of x z, zx, is a sum over m up to x. And then I want the indicator function of this thing being 1. In other words, I want this indicator function sum over divisors of n, but n is the GCD of these two things. In other words, a divisor of this and a divisor of this.
Divides both.
So d dividing m times m plus 2 and d dividing the product of the primes up to x, up to z, of Mobius of d.
At the cost of studying Mobius.
Exactly. So let's reverse orders. It's number theory. You got two sums. You got them the wrong way around. So I'll put a sum over d. If I don't specify anything, you'll see that all sums are divisors. Well, okay, I'll put it here, but we'll get pretty bored. Every number that will appear will be square free and will be a divisor of, consist only of primes less than z.
Yes, that's true.
Okay, Mobius. And then a sum over m up to x. M has to have this property. So I'll put the indicator function that m times m plus 2, m times m plus 2, technology time, left plenty of room over here. Beautiful. Okay. Let's make that a little bigger. The indicator function of m times m plus 2 being congruent to 0 mod d. Okay. Now this is very elementary to estimate. There's some residue classes mod d. Let's say there's a w of d residue classes mod d. And then every x over d numbers lie in that residue class.
Oh, and d was just taken to be.
D is this product.
It is square free.
D is square free. That's right. We only care about square free d's.
Oh, okay. So this WD means just a phi function for.
Well, it's not quite the phi function. So WD is the number of m mod d so that m times m plus 2 is congruent to 0 mod d.
Oh, so you're just taking the solution of set of
Yeah.
this mod d.
How many arithmetic progressions are there mod d? In each arithmetic progression, we can count how many points there are up to x. There's x over d of them. In fact, the better way to write this is this is the number of arithmetic progressions. There's x over d points in that progression with an error of if I tell you a progression, how many points, how much could I be off? How many numbers up to 1,000 are divisible by 37? It's 1,000 divided by 37 with a rounding error. 1. Okay. When we give upper bounds, we can't say 1,000 over 37 itself. I mean, we need the plus 1. This is a +1.
Okay.
Okay. And as you'll see, this +1 kills everything. In fact, it has to kill everything. Okay. Let me come back to why. So this is Legendre's attempt. This is Legendre's attempt. This is now inclusion, exclusion. We have plus signs and minus signs. We're adding in the multiples of 2. We're subtracting. We take, when D is 1, we just get all the numbers. Then we take off the multiples of 2 when D is 2, because Mobius of 2 is -1. Then when D is 3, Mobius is again -1. We take out the multiples of 2. But when we get to 6, Mobius adds it back in. So that's this inclusion, exclusion that Mobius is capturing. Okay, but this will not work. This fails miserably. And the reason it fails is that look at how large D can get. How large can D get? How large can D get? Well, it can get as large as PZ. Now, how large is PZ? Remember, PZ is the product over the primes up to Z of P. How big is this? Well, let's see. If we take its log of PZ is a sum over primes up to Z of log P. Ah, beautiful. That's exactly what the prime number did. Tells us. This is of order Z. So this thing is of order e to the Z, which is e to the x to the 1/3. It's absolutely ginormous relative to what it's supposed to be counting. So that big O of 1 will swamp everything. So D gets way too big. This D. So D gets way too big to be able to handle anything approximating this.
I'm a little slow. How did we set up that estimate again? I'm like,
sorry, this estimate?
no.
Where are you pointing?
The WD one.
Ah,
I'm just,
okay. We want to know how many M there are up to X, so that M times M plus 2 is 0 mod D. D is fixed. For each fixed D, we want to estimate this.
Okay.
Okay. So what we'll do is, well, how many in the residue class Z mod DZ? How many residue classes? How many residues are there that satisfy this? Whatever that number is, we'll call it W of D.
Oh, okay.
For each residue, how many numbers are there up to X that lie in that residue class mod D? How many numbers up to 1,000 are 12 mod 37?
No, I see.
There's 1,000 over 37, right? And then this is how many arithmetic progressions there are. So that's how many errors we introduce. Okay, so this idea again fails, and Legendre didn't get it right. So the key idea in Brun is to give weights. Brun and Buchstab give approximations, give weighted approximations to this thing, to this sum. Instead of having a pure sieve, you have something that's a worse sieve that does a worse job of understanding what these numbers are at the cost of upper and lower bounds. But let me give you Selberg's version of this, which is much more elementary and totally insane and works beautifully. Okay.
How do we know that Legendre did this and it failed? Did he like write it up?
Well, he said, here's this inclusion exclusion principle, and in some very so if Z is tiny, if Z is not a power of X, if Z is like log X, a half log X or something, then okay, yeah, let's point this out. Remark: if Z is only a half log X, then this is perfect. Then PZ is not too big. Then there's no problem with D, with large values of D. D is less than whatever, root X or something, right? E to the half log X. This is E to the log of X to the half.
And then,
okay.
Wait, then why doesn't this work?
Well, what does it give us? We have numbers M so that its smallest prime factor is of size log X. M is of size X. Doesn't tell us anything. It gives us some bound on how many, but the number of prime factors can grow with X. It's not a bounded number of prime factors. Okay. Gives us nothing. Gives us, well, next to nothing towards the sieve.
Oh, so what you're saying is that, wait, so what does this estimation become if we choose z equals 1/2 log x? What are we estimating concretely?
How many numbers up to x have, well, m and m plus 2 have no prime factors less than log x.
Oh, and then you're saying, but we need to count all primes.
We need to sieve out all the primes up to x to the
X to
1/3,
not log.
not log.
Oh, okay.
Okay. So we need a power here. We need z to be a power in order to get something like Brun. But if z is a power, then e to the z is way too big in order to be able to execute this. Okay, so here's Selberg's crazy idea. Okay, so Selberg's crazy idea is the following. Hey, Selberg's crazy idea is this inequality, a sum over divisors of some totally arbitrary function squared if lambda is any sequence, not complexes, reals, and lambda of 1 is 1, then this identity holds.
Okay, no multiplicative, no nothing. Just that?
Just that.
Is that true? It sounds very wrong.
It sounds very wrong. When you first see this, it sounds very wrong. Now let's parse it. When n is equal to 1, if n equals 1, this side, there's only one divisor. The left-hand side is 1.
It's not crazy.
It's crazy. And the right-hand side is also 1 squared. I said lambda 1 is 1. That's the only thing I said. Right-hand side is 1. So it checks. Yeah. So right. First it looks wrong. First it looks wrong. First, I don't know why I'm writing this. First it looks wrong. Then it looks stupid. Then it looks, stupid, useless. And in fact, it won't be. So let's stick that in. Instead of opening the reversing orders here, let's stick it in. So S of xz is bounded above by a sum over m up to x, m up to x, and I'll stick in this thing, a sum over d dividing. If you recall, that was d dividing the GCD of m and m plus 2 and p of z.
And these lambdas are going to be your weights.
That's right. And d dividing p of z of lambda of d, whatever lambda is, squared.
So now from something we can barely control, we have something
Yeah,
full control of.
Well,
And
let's
across the
see.
square.
Let's see. So let's open the square. So let's open the square. So we have a sum over d1 and d2. They're both divisors of pz. I'm going to stop writing divisors of pz. I have lambda of d1, lambda of d2. And then I have a sum over m less than x. And again, just an indicator function that m times m plus 2 is 0 mod d1, and m times m plus 2 is 0 mod d2, which of course is the same thing. These two things together are the same thing as m times m plus 1 is 0 mod the least common multiple of d1 and d2. Okay, this looks bad. This looks very bad. Here's why it looks really bad. The size of before the divisors could be of size p of z. But now it's like squared. Yeah, so if the d's went up to capital D, now they go up to capital D squared.
Right.
So it's even worse. The problem has been made worse by squaring.
But we have the freedom of choosing lambda, right?
But we have the freedom of choosing lambda, and we can choose lambda to have support much smaller than p of z. Okay, but we have freedom, almost complete freedom, It needs to be 1 at 1. That's its only condition. Almost complete freedom to choose.
Let's be real.
Yeah, lambda will take it to have smaller, much smaller support, so that this squaring doesn't ruin everything.
An idea like this had been used before this proof by Selberg?
Shockingly, no. Shockingly, no. Yes, exactly. That's right. That's right.
I did some work on this file.
If you, yeah, when he proved the positive proportion of zeros on the line, yeah. In fact, the notation is identical. Anyway, so let's go into this. We know exactly what this is. This is however many residue classes there are that satisfy this equation in the LCM of D1 and D2. So this is equal to sum D1, D2, lambda D1, lambda D2. So the lambda may as well be supported on square free numbers. The only numbers that arise are square free. And then this is how many residue classes there are in the LCM of D1 and D2, satisfying this relation, times X over that residue class, D1, D2, plus big O. Okay, exactly the same as before.
This could be exactly +1, right? Precisely the bound +1.
Well, as an upper bound, but the lambdas might be positive or negative.
Yeah, so the other, yeah, so you give it off, we go. That's good.
But in fact, let's immediately write this as X times something I'll call Q plus an error where Q is exactly this factor sum over D1, D2, lambda D1, lambda D2, omega of the LCM D1, D2 divided by D1, D2. Well, this Q, right, this Q is a different Q. This Q is for quadratic form. You see, we have a quadratic form in the lambdas. This is a quadratic form in the lambda of D, which are distinct, which are variables. What's the error? The error is a similar thing, a sum over D1, D2, lambda of D1, lambda of D2, omega of D1, D2, and big O of 1. In other words, we're going to have to put absolute values here, but what it doesn't have, what this error term doesn't have, is it doesn't have the X. So it's already going to be a much smaller order of magnitude. And once you see how to analyze Q, and once we've chosen the optimal lambdas to minimize Q, we'll see that the error term is orders of magnitude smaller. Okay. So, well, we have a quadratic form. What should we do with it? We want to make this upper bound as tight an upper bound as we can. You have a quadratic form. Find its minimum. Yeah, we need to minimize. So what we need to do now, once you have that one idea about the square, it's high school.
Well, because this is a quadratic form over the reals, right?
Over the reals.
So you just find the minimum.
Yeah, you need to minimize Q with respect to these lambdas, lambda D, subject to, our only restriction is that lambda 1 is 1. Okay. It's not entirely trivial.
You have a lot of variables, right?
There's some variables going around, yeah. So there's a variety of ways of doing it. One way is to diagonalize the form. Okay, so to make our lives easier, to make the analysis easier, let's diagonalize. So here the D1 and the D2, there can be cross terms. It's not like a coefficient times, if it was like, if the quadratic form was alpha y squared plus beta z squared, whatever. then it's really trivial to diagonalize.
You're getting all the cross terms.
We have a lot of cross terms. So we're going to do a little bit of Mobius inversion type arguments to get rid of the cross terms, because there's cross terms in this LCM. Okay, so let's see how to do that. Okay, let's say that the GCD of D1 and D2 is equal to C. And let's say D1 is equal to A times C and D2 is equal to B times C, with A and C coprime, A and B coprime. I mean, they're all coprime because D1 and D2 are square free. So A and C are coprime, B and D are coprime. That's automatic from the support of lambda. But the fact that A and B are coprime, that's not automatic. Okay, so we'll sum. So Q, okay, so Q is a sum over A's and B's and C's, A's and B's and C's. There's a lambda of AB, AC. C is the thing in common, right? What's the LCM? The LCM of D1 and D2? ABC. That's exactly the point. Okay, so lambda of D1 is lambda of AC, which means A and C are coprime. Lambda of D2 is lambda of BC. You see, this is the thing where the C is where they're mixed up with each other. That's what we need to get rid of. And then W of ABC divided by, divided by ABC.
I guess that one's like you want to work from then
That's right.
square of
That's right. But because we have this, I'm here. But because we have this LCM term, they're intertwined and we need to de-intertwine them. So the one thing that I haven't taken into account is the fact that A and B have to be coprime. That doesn't follow from the other things that are written here. Okay. How are we going to catch this coprimality? With a Mobius. Okay. So I'll write this as a sum over, I need a new variable, L dividing A, L dividing B, Mobius of L. Let's reverse orders. I'll put the L all the way on the outside. Again, A, B, C were all divisors of PZ, L is a divisor of PZ. So it's a finite sum, but I won't keep track of that all the time. I have Mobius of L, and then a sum over C, and then a sum over A that's 0 mod L, and a sum over B that's 0 mod L, lambda AC, lambda BC, WABC. By the way, W is a multiplicative function, and if they're all pairwise coprime, then this is the same thing as W of A, W of B, W of C. Yes, W, if you remember what W or omega, whatever, omega is counting how many numbers mod D satisfy this equation. But this is a multiplicative function, because Z mod D decomposes into Z mod the products.
For the whole prime
For the whole, yep. So this is if D is square free, this is a product over the primes dividing D of W of D. Chinese remainder theorem. Chinese remainder theorem.
Our D's are all square free here.
That's right.
There's nothing.
Okay. Then I have W of A, which I'll put over here. W of A over A, W of B over B, W of B over B, and W of C over C. Now something fun happens. I should have, if I was smarter, I would have done this slightly slicker. Sum over A that it's 0 mod L, W of A over A, lambda of AC squared. Because of the symmetry of A and B. This thing is completely symmetric in A and B. It's just two copies of the same thing. So we're on our way. The only thing now is that there's a C inside both of these things, and we want to get rid of that C. Okay, so here I want to make a change of variables. God, I need a new letter. A, C, I can't use D, E. Is E a bad letter for H? H. H is AC. Okay, let's make this change of variables. If H is equal to AC, then this sum is over L, Mobius of L, a sum over, yeah, let's sum over H. Let's sum over H. I hope I get this right. And then divisors, C dividing H. Where's L? L is down here. I want to say A is 0 mod L. Yeah, this is a little tricky. Let's see if I can get this right. So this is going to be lambda of H. W of A, that's what I want to do. Great, great. I want to make an AC in here. So let me bring 2 copies of this inside. But then I owe 1. Okay, so let me do it like that. Then I'll owe 1. So I'll owe a factor of C over W of C. By the way, W of C is never 0. And then I get a sum over A congruent to 0 mod L of W of A, W of C over AC, lambda of AC squared. Okay, good. For different sequences, you could have different W of C 0. Yeah. Okay. Then you don't, if you have a WC that's 0, that's right. The PZ has to take out that prime. WP could also be P, which also would be bad for other reasons, as we'll see. Okay, so now I want to make, now everything that occurs here is a function of AC.
But then over here, WC is not going to be 0 because 0 is just a solution, right? Or my like.
WC is not going to be 0. Yes.
Oh, yeah, you're right.
Yeah.
Right. Okay. Yeah.
Yeah.
Now we're looking at
WC being WP being of size P would be bad. We'll see that in a second. Anyway. Yeah.
Right. Nothing.
In fact, I mean, it's
2 solutions.
it has 2 solutions except when the prime is 2. In fact, that's an important thing to note. Where are we here? Yeah, I think I have room. Yeah, exactly as you said. W of P. Let's record the fact that W of P is 2 for most primes. Is 2. Yeah, W of P is 2 if so if P is equal to 2. If P is equal to 2, then I have M times M plus 2, which is just M squared is 0 mod 2. The only number that squares to 0 mod 2 is 0 itself. Okay, and if P is less than Z, when I multiply this out, then I get 2. And if P is greater than Z, I get 0. I don't know if we want to record this or not. In other words, we're summing over these divisors, but the divisors only have factors less than Z. And so if we want to record, if we want to make a function, I mean, this doesn't really make a difference.
You're saying there's 2 solutions because of quadratic reciprocity?
I'm making a function W of P that captures this condition, but the only place where this support is on primes less than Z.
Yeah. Then why are we
That's
getting 2?
Oh, 2, because you M is either, if your P is a prime, then M is either 0 or -2 on P. So the number of solutions is 2. Which, by the way, this 2 is a very important number. The fact that it occurs for all but a small number of primes. This is going to be the sieve dimension. And it's going to be closely related to the fact that we save a log squared. I'm claiming this log squared. Did you say reciprocity? Yeah, here I'm just saying M is 0. If P is a prime,
Oh,
then which of these two is
Yeah,
divisible
yeah.
by P? Either M is 0 or M is -2.
and also the solutions are just
That's-
taking zeros and,
Yes.
okay, yeah, no.
Yeah.
Oh my God.
Okay. So,
Right, if it's not mod of prime, it's mod something else, then.
okay. So let's see if I can get this right. I have a sum over L, Mobius of, yeah, let's do it like this. I want, see, A has to be 0 mod L. That means AC has to be 0 mod LC. Thank you. Right? If A is 0 mod L, then AC is 0 mod LC.
Sure.
Okay. So I want to make, I guess I want to make LC the new parameter. Let's make LC the new parameter. So I'll call that, okay, I'll call it H. Let's say H, we're summing over H. LC, H is LC, let H equal LC. So as I sum over all possible things, I'm summing over all possible H's. L is a divisor, so sum over L dividing H. I have Mobius of L, and C is the other divisor. So C, in fact, let me write this as C dividing H. C dividing H, Mobius of L is H over C. And then I can keep this as C over W of C. And then I have a sum over the AC variable is now one variable of F congruent to 0 mod H. H was LC. And then I have W of F over F times lambda of F all squared. Okay. And now I claim things have been completely diagonalized. This is a coefficient that only depends on H. Let's call this, I don't know, alpha of H. And this also only depends on H. Let's call this Y of H. And now we've written Q as a sum over H, some coefficients alpha of H times Y of H squared. We've diagonalized Q. This whole thing was Q. This whole thing was Q. And we just made a couple of changes of variables until we got down to some coefficient. It's a function of H. C dividing H, Mobius of H over C, C over WC, times the square of some linear, this is a linear change of variables, linear change of variables from the variables lambda. It's just some linear combinations of lambda.
Oh, yeah, so our lambdas were variables, and so now.
Now our y's are variables. Okay, so now we're going to want to minimize Q subject to, well, the original constraint was that lambda of 1 is 1, but we need this in the y variables. What is this in y? Need this in y. Need this in the y variables. Okay, so we have to, how do you invert this linear change of variables? So here's another, make this an exercise. Exercise. Mobius exercise in Mobius inversion. If let's say f is a function, doesn't have to be real valued anymore, and is supported, has finite support on square frees. Okay, and let G of n be a sum, be defined as the sum over progressions, multiples of n of f. Okay. Then G also has finite support and support on square frees. That's not hard to see. And how do I get back to F? If I take G of A, multiply it by Mobius of A, and sum over A congruent to 0 mod n, I will almost get F, except with a factor of Mobius. So this is Mobius inversion, not on divisors, but on progressions. It's the other kind of Mobius inversion. So this is Mobius inversion, not on divisor sums, not on divisors, but on progressions. Sort of the dual Mobius inversion. Okay. Should we do this exercise?
It's fine.
It's not that hard. Should I show you some of the ideas? It's a good exercise. It's a good exercise. You stick in, okay, hint. The hint is you stick in the definition of G, insert definition of G, insert definition of G, reverse orders, and hopefully you've had enough experience with changing variables in modular and change variables. And you'll get to the classical Mobius inversion formula. Okay. So how does this apply to us? Well, look at what y is. Y is a sum of some function on progressions mod h. So I can get back to lambda by this inversion formula. Since y of h is a sum over progressions, I don't remember what variables I was using. F. That's a good point. That is a very good point. If I could get zoom out of the way, I could copy and paste. Beautiful. Copy. Paste. Amazing. Love technology. When it works. Don't need that, don't need that. Let's grab that. And put it right there. Let's move everything over here. Since y is a sum over progressions mod h of something, I'm going to use this inversion formula. We can get back to lambda. Lambda of n is Mobius times a sum over progressions. Yeah, well, we used a for something else, but hopefully you'll forgive me. Of Mobius of a times y. Sorry, it's not lambda, it's lambda times omega of n over n. This is the function that captures y. Y of a. Yeah, that's the inversion, linear inversion. Okay, so but I only care about this when n is 1.
Yeah.
I only care about lambda of 1. So I have omega of 1 is 1 over n is 1, lambda of 1, that's supposed to be 1. On the other hand, it's Mobius of 1 is 1. A sum over a congruent to 0 mod 1 is over all a. Mobius of a, y of a. So this is our condition. So minimize q subject to the linear constraint. This is our new constraint. Sum over Mobius of a, y of a is 1.
Yeah, with the advantage that now we can deal with the y's in diagonalized form instead of
Exactly, and q is already in diagonal form. It's alphas times y's. Sum over a h. Let's call it a h of alpha of a, y of a squared.
Is it clear that you can like diagonalize a form easily to do this sort of computation, or
Well,
does it just so happen to be easy?
in general, even if we didn't diagonalize, you could still do the analysis. It would just be a bit more annoying and you have to think a little harder and tedious, yeah. But the fact that we got a quadratic form is right here. This thing that we called stupid is exactly the thing that gives us a quadratic form, which we can minimize subject to a linear constraint.
And like, you know, because it's a real positive that you could in principle of value on it. But I guess what you're saying is like the formula.
Yeah, it didn't have to come out to be a nice formula, but yeah, exactly as Lewis said it.
Even had it come out ugly, you'd still be able to do this and move on.
And in other applications, that's exactly what happens.
What are the constraints on A?
The constraints on A, yes, all the way down here. These A's, as with everything else, these A's are divisors of PZ.
It seems kind of magical.
Right. Okay.
And the YA will have compact support because the lambdas have compact support. In fact, they'll have the same support as the lambdas. So we haven't talked about the support of lambda, but of course we're going to localize the support of lambdas.
And something that never goes to kind of to that's kind of magical about this is like all we're doing is optimizing Q, but then like, it'll like automatically that
Yes.
because there's still 2x plus Q, and it turns out that like the optimal choice. Maybe I'm like taking it down.
No, go ahead.
But it just by optimizing Q, like
It's good enough for the
principle, that can be really bad for E.
Right.
And it's sort of just a gift that the optimal choice.
Instead of like when we were doing circle method and you had the minor x and major x, there was a lot of like interaction.
That's right. Here E will be of much lower order compared to there's an X here, but there isn't on E. So already this is going to be like a Z or something. X, this is going to be like X to the 1/3.
It doesn't seem crazy that if somehow Q would take care of E, considering how similar they are, I guess. You know, they have these lambdas in common.
Yeah,
and it's, I don't know.
here we have to put absolute values.
Yeah.
So yeah, in my mind, I mean, it is true that the lambdas that minimize this also happen to minimize this, but this is the one that's got an X in front of it. So you know, the difference between these two is this 1/d1, d2 that's missing here. So that's going to bump everything up by a factor of d squared if d is the support of the lambdas. So as long as that d squared is less than x, so we
still under the optimization.
under the optimization, we should still be able to get, yeah,
Very nice.
stay under. Okay. Well, how do you do this? So we have a quadratic form Q. I'm thinking of like, you know, something like this. We have a linear constraint. Okay, so we have this sort of subspace and we need to find the minimum. You guys know how to do this? My favorite way is Lagrange multipliers. Right.
That was going to be my first guess.
Perfect. Okay.
Calc 3.
Yep, exactly. Calc 3. So we're going to set up a Lagrangian, which is in the y variables, and an extra variable theta, which is the thing that we want to optimize, this alpha of A times y of A squared, minus theta times the linear constraint.
What is that dot? Are you taking
That dot is typo. Schmear. Theta times the linear constraint, sum over A Mobius of A, y of A minus 1. Okay, so you set up this Lagrangian, and what you want to solve is that the partials of the Lagrangian with respect to each of the YA's is 0, and the partial of the Lagrangian with respect to the multiplier theta is also 0, which of course recovers the linear condition. Now, what do we get for the Lagrangian with respect to any of the YA's? Because it's diagonal. Sorry, Nick.
What's the symbol after you have mu of A, y of A minus 1 in parentheses?
-1, yes, that's just the linear constraint. That this minus this is
okay.
0. So I put a multiplier theta in front of that.
That makes sense. Thank you.
Yep. So we have this thing. Now the A's are all independent. That's the beauty of diagonalizing.
So you only one term.
Yeah, I just get 2 alpha of A, y of A from here, minus theta times mu of A, y of A. No y of A. The derivative of y of A is 1. And that's supposed to equal to 0. Okay, so we know what y of A is. Y of A needs to be, what is it? Theta Mobius of A over twice alpha of A. Okay, and our linear constraint, is that the sum over A, Mobius of A, y of A,
Would be expressed over the seed, right?
yes, the alpha is this expression here. Now, we should probably analyze it because we're dividing by it.
Right.
Okay. Let's just finish this calculation, then we'll analyze and I'll convince you that you can divide. Yes. Where were we? I'm putting in the linear constraint that Mobius of A times y of A is equal to 1. But the times y of A is times theta Mobius of A over 2 alpha A is equal to 1. I'm just sticking this in here and using this.
Oh.
I'm just taking the linear
Oh,
constraint.
okay.
Sum over A, Mobius of A, y of A is 1. That's this last
Right.
derivative. Okay, so that tells us what theta is. Mobius squared, everything in sight is divisors of PZ, so everything's square free. Mobius squared is 1.
Wait, but if you do the derivative and the theta doesn't go.
I took a derivative in theta.
Yes, then the theta should.
The theta's gone. I just get that this thing, I just get back the linear constraint.
Oh, yeah, so you wrote and theta.
Ah, that theta is when I stick
Oh,
in the
this way.
YA,
Okay,
that's a
okay,
constant that pulled out.
This-
Yep. So theta is 1 over, so let's give this thing a name. Let's capital A, can I do that? Capital A be a sum over little a, 1 over alpha of A, which is what comes out here. So let theta be half capital A. Okay, then y is equal to, theta is, other way around. Theta times a half times capital A is 1. So theta needs to be 1 over or 2 over capital A. Again, I have to make sure that all these things are non-zero. We'll do that in a minute. So when I stick that in here, I get that YA is equal to Mobius of A times 2 over A times a half and an alpha in the bottom. That's the final answer. All right, let's analyze some of these things.
Yes, we're good as long as the alpha is not zero.
As long as alpha A is not 0, as long as big A is not 0.
And then,
Okay.
Right, alpha.
And by the way, what is Q? So what is the minimum value? Yes. We'll see in a second. Yeah. We'll see in a second. So suspend your disbelief for just a second. Q, which was a sum of alpha of A, y of A squared. Now we know what the y of A's are. The y of A's are this.
Where does little a range for the sum of big A?
All of the ranges of the summations or divisors of PZ.
Oh, this that's it.
The y is Mobius of A over A times alpha of A squared. I'm just sticking in what the y's are. But wait a second, that Mobius squared is 1. The 1 over, I get a 1 over A squared times the sum over A, I get an alpha A over alpha A squared, so that's 1 over alpha of A.
A.
That's A again. So I just get 1 over A.
Yeah, I guess usually I was about to say, usually there's some like a guess, right? What the solution would be.
Yeah, it's.
Like,
Yes.
tell the calc students, like,
Yes.
yeah, if these are similar, then you would guess that.
That's right. If you have all these, yeah, think about it. If you have all these coefficients, what you want to do to minimize this is to make them all roughly of the same order of magnitude. Right? If you have a sum of x, some coefficients times x's squared, then where's that minimum? It's where everything balances.
Right.
So this is exactly the thing that balances this value 1 over A times that exactly is the thing that balances and you get this one. Okay, so we have to understand what all these things are. Let's go back to alpha. What is alpha? Alpha is this thing. Magic. Magic, magic, whoops. Magic, magic. Okay, copy. Let's work on alpha.
Divided some with,
Paste.
so.
Right. Okay,
So it looks like invert this,
or just evaluate it. Okay, so recall what alpha is. This is alpha. It's a sum over multiplicative things, so it's enough to evaluate this at the primes. What is alpha of P? Alpha of P, when H is a prime, there are two divisors. One divisor is 1, and the other divisor is P. When C is 1, I get mu of P times 1 over W of C is 1. When C is P, I get mu of 1 times P over W of P. Okay, so what is this? Mu of P is -1. So I have -1. I have this W, mu of 1 is 1. W of P, so I'll write this as P minus.
So you said WP being P would be bad.
Yes. Why would it be bad? Let's think about that. Why would W?
Dividing by 0, that's sometimes.
Yes, that's right. So I certainly don't want W to be 0, but W sort of can't be 0 unless you're just trying to solve some equation.
Alpha P would be 0, and then you're dividing by alpha.
That's right.
Yeah.
That's right. So why? So W of P is positive. It's at most P. It can never equal P. Why can't it ever equal P? Well, we know what WP is in our case. In our case, W of P is 1 if P is 2, or 2 if P is greater than 2, but less than Z. Right? That's the number of, but what if you were trying to find primes, if instead of twin primes, you wanted to find triplet primes, M times M plus 2 times M plus 4, all being prime. You get 3 solutions. When P is 3, that 3 solutions is all the possible values. W of 3 would equal 3. And you get that alpha P minus W of P is 0, and you wouldn't be able to divide by alpha. You're in trouble. You're in trouble because there are no triplets primes. One of these numbers has to be divisible by P. Okay, so you'd be in trouble for a good reason.
Keeping 3 here.
Yes, exactly the place. So you would need to remove 3 from the set of primes that you're sitting. Exactly. It's yeah.
Does it cost too much complication?
What's that?
Does it cost too much complication?
Like say, oh, remove 3 from your.
If you have a K-tuple, this is the Hardy-Littlewood K-tuple conjecture. If you have a K-tuple that fills out all of the residue classes, mod sum prime, that's it. You're dead. There's no way to have infinitely many primes in that sequence. Because no matter what the residue class is, you're hitting the prime somewhere along the sequence. You can't have all K of those simultaneously being prime. So that's exactly this condition. The W of P has to be strictly less than P. Okay, so the alpha P's are indeed positive, both because the denominator doesn't vanish and the numerator doesn't vanish, and the numerator is non-negative.
We're not considering them at prime powers.
We don't even need, yeah, there's no prime powers in sight. We're on square freeze.
Yeah.
Okay, so the,
I think it should be easier to remove but you would take more technical. Right? Because then like case and open for
When you're saying is to give a similar asymptotic to say what Selberg is doing here.
well, you can work out the upper bound, the Selberg, this is called the lambda squared sieve. Did I ever say that? I don't think I said that. It's called the lambda squared sieve. Yeah, for exactly. Yeah, Selberg's idea is called the lambda squared sieve.
Oh, capital M, that's C.
Yeah, for exactly, I mean, I don't know, for this reason.
Oh,
Um,
okay, yeah, as in you're taking, yeah.
What is it? Quadrature A positive. This is a
Yeah.
chapter in Friedlander
Oh,
Ivanitz.
yeah.
Right. So I didn't finish the sentence, but no primes, no chance of having triplets, all three of these simultaneously be primed. Yeah, you need to do something like take it out. Okay, what about this factor A? So A, see, once I start using technology, I can't stop. That's the problem. The alphas are fine. What about the A's? The A's are sums. Well, okay, they're positive. Yeah, fine. They're not zero. There's no problem with dividing by them. But let's evaluate it exactly. This is the sum. When you have a divisor sum, you have a sum over divisors of this, the product of all the, this is the product over primes dividing PZ, which is the same thing as to say primes less than Z, of 1 plus 1 over alpha of P. So think about what happens when you multiply all of this out. You get to choose either 1 or 1 over alpha P for each subset of these primes, which is exactly
The standard Euler product.
standard Euler product. Yep. So let's work out what this is. Okay, so I have a product over primes less than Z of 1 plus, okay, 1 over alpha of P is omega of P over P minus omega of P. All right, I'll put the 1 plus and we'll do it in 2 steps. So this is a product over primes less than Z.
Alpha of 1 is in fact 1.
Alpha of 1 is in fact 1, yes.
Because otherwise, then you'd have to, yeah. Then
Yeah.
have 1 plus within.
That's right, that's right. Alpha of 1 is 1. So now I have P minus, so I'll make this 1, I'll combine the denominators. So I just get P over P minus omega of P. Right? Which I can write as a product over primes up to Z. I want to flip this. I want to flip this as P minus WP over P, which is 1 minus W of P over P. Now, wait a second. For all primes except 2, so when P is 2, I get a 1/2 here. It's a chunk of, it's a partial Euler product. Yeah, primes greater than 2 up to Z of 1 minus 2 over P inverse. Okay, what do you know about sums like this? Products like this. So that 2, by the way, this is again the sieve dimension. The same sieve dimension. Remember where it came from. It's how many residue classes mod P are there that we need to break into for a given prime. So this is of the same order of magnitude as the product over primes up to Z of 1 minus 1 over P to the minus 2. Why is that? Well, what is this? It's a product over primes up to Z of 1 minus, I'll keep the inverse outside, but when I have 1 minus 1 over P squared, that's 2 over P plus 1 over P squared. But this 1 over P squared, the difference between this sum and adding a 1 over P squared, the 1 over P squared converges. So this is of the same order of magnitude as that, up to constants above and below. So again, this 2 is the sieve dimension. Now, do you guys know what the, have we talked about Mertens theorem? So now we're just looking at zeta.
Nope. Oh, not bad.
This is not my,
Technology is taunting you.
yeah. All right. We're almost there. Let's just try to finish it and get out of here before more stuff happens. Mertens theorem says, you see, if you have a, let's compare. If I take a product over all primes, 1 over 1 minus P to the S inverse, that's exactly zeta of S.
Right.
And I know that zeta of S is like 1 over S minus 1 plus lower order things. So I know the rate at which this blows up as S goes to 1. Yeah, we know how this blows up as S goes to 1. But what if we set S equal to 1? Well, of course, that's infinity. But we restrict the product instead. That's exactly what Martin's theorem is, which is much easier than this, which is also not hard. It says that this blows up, and the rate at which it blows up, anybody know? It's log z, as z goes to infinity. Yeah, that's interesting. I've never thought about that. In my mind, these are really two quite different things, but maybe there's a way to do that. Yeah, to me, truncating the Euler product, like really, especially if it's a divergent Euler product. Yeah, exactly. So this is one kind of truncation. This is kind of a mollification, amelioration, whatever you want to call it. So there are two different ways, I would say, of approaching the blow up of zeta at 1.
How would you go about proving something like that?
It's a pretty elementary thing. In fact, it's not so. Okay, let me not say it's not so far from what Euler did in showing some of the reciprocals of the primes diverges.
Okay.
It's really not so far from that. All right, so we have this log z. We're almost done. Well, that means that A is of size asymptotically. Here isn't the constant 1. Oh, you're right. It's gamma. The Euler, e to the gamma, e to the 2 gamma, 2 e to the gamma. All right, let's be pedantic because it actually is important. You're absolutely right. Come on, 2 e to the gamma. No, I think you're exactly right. And this constant is like 1.12 or something, but it's not equal to 1, which tells you that when you do the sieve naively, you're going to get the wrong answer. The error terms do indeed amount to more than the main term.
Is it philosophical importance?
This has philosophical importance. Yes, the fact that this is not equal to 1 caused quite some confusion in the 1800s. Okay, or 1700s. So A, of course, that was. I mean, maybe I'm being anachronistic because, yeah. So A is of order. What's the order of A? A is this thing squared. So it's of order log z squared. And what was Q? The optimal value of Q is 1 over A. So the optimal value of Q was 1 over A. So Q is less than 1 over log z squared, and z was a power of x. So Q is 1 over log squared x. And so the number of prime tuples up to x is x over log squared x. A is the square of this because of the sieve dimension. I keep saying this 2 is exactly the sieve dimension. So let me.
This 2 originally came from that omega function.
Exactly.
So had this all been cubes, say for example, if there were exactly 3 classes?
Yeah. Then exactly the number of this goes right back to Leonidas asked about this independence. Here's where we're seeing that independence. That this 1 over log x for each of the primes. If you wanted to catch m and m plus 2 and m plus 4 and m plus 6 rather simultaneously being prime. Now there's no local obstruction at 3. And this would tell you that it's of size x over log cubed x for exactly this same reason.
Really? And so it really has to do with how many progressions you're breaking it up into?
Yes. So what I wanted to showcase with this, we're done. I just wanted to because we had the sieve as a black box last time. So I want to showcase that if we have a good understanding of the distribution of the set that we're sifting in progressions.
And so general sifting techniques use something like these lambdas.
Exactly, yeah. So instead of upper bounds, if you want lower bounds, then you have to be very, then you don't do a quadratic sieve, you do something that stops the inclusion, exclusion at some point, but not other points. It gets very, very technical very quickly.
How to deal with this Mobius function.
How to deal with the Mobius function, replacements for the Mobius function in various parameters at various scales. There's, I mean, entire semesters worth of courses.
If the Mobius function were easy to understand, then like splitting theory would be very, very easy to do.
If the Mobius function were easy to understand, a lot of people were out of business. There are a lot of people who make a career out of the fact that the Mobius function is not easy to understand, and thank God for it. We want some secrets that we have to, uncover.
I mean, that's what I was trying to say at the beginning, that the fact that the naive thing doesn't work for twin primes is what makes people get a lot of prizes and jobs and stuff.
That's right.
Like that, and
That's right. That's right. Having some mountains to scale. If there are no mountains, then what are you supposed to do? Yeah, we need.
Were an issue. Then like Fermat's last theorem would have been easy to.
Yep.
Deal with.
Anyway, so that was just a very quick crash course. Hopefully you got something out of it. Of one small aspect of sieve theory in a very concrete example.
And then what happened to the error again?
We didn't analyze the error, but now that we've chosen the y's,
Would the error come out to?
the error will come out to a much lower order. So we've chosen the y's, which means we've chosen the lambdas. And when you analyze this, you see that it's.
I think you saved one. You saved 1.1.
I think the error is bounded. Let's see. So it depends on how big we want to take the support of the lambdas. In fact, we've taken the support of the lambdas in this construction. Where are we? The support of the lambdas follows from the support of the y's. The y's are supported where alpha is supported, and alpha is supported. Remember, how do I want to say this? Well, it's either this or it's zero. It's not. Yeah, 1 over alpha. Okay, let's put it this way: 1 over alpha is WP over P minus WP. And we set WP to be 0 once P is larger than Z.
Oh, so you're saying C is.
Yeah, so exactly. If Z, we don't have to take, at this point, we don't have to take Z to be P to the 1/3. We could take it even smaller, but even if it's P to 1/3, the worst that this should get is X to the 2/3. We should get a power savings off of here, not just a log savings. It's much smaller. I have a little write-up about this that I'll post.
So you're okay. So the error is not going to be an issue, even though it's. So you do a similar analysis, except you don't have that LCM like floating around.
Well, now you don't have a choice. Now there's no. You have to go back to what the lambdas actually are.
By converting them from the y.
By converting them from the y's.
And then just
analyzing this thing directly. Yeah, and putting in absolute values.
And then for the sieve dimension thing, I guess I'm having a hard time understanding its significance still. So it's like you're saying, at what time did this become from number of progressions to a power we were taking?
Right. So the number of progressions was right here, which was 2. Where's our W? Right here. Okay, so this was 2.
Where did this come in?
Where did this come in? It came in to the A. A was this, which looked like this. This capital A that comes out, the sum over the 1 over the alphas.
Oh, because
comes out to
is greater than 2. That's how we're getting 2 out of that.
Yeah, we took out the prime 2. For all the other primes in this range.
I guess pretty much W is like kind of holding all the information, right?
Yep. Yeah. And so what people do in sieve theory is they just axiomatize this instead of doing it to a particular, instead of applying it to a particular function, they just say, what were the general principles that were, so suppose we now have some.
Boom, these sort of constraints in your function.
Exactly. Suppose we have a function so that when you look at the multiples of D, you have some function W of D over D, that function should be multiplicative.
That's how you get
And
these
an
black
error.
boxes.
That's what the black
and
box, exactly.
Just pushing this analysis as general as you can.
Yep.
So this is very interesting. Wait, and then the fact that we got this Euler product came from what?
Well,
Came from the multiplicativity of,
from the solution, I mean, this 1 over alpha A, we worked out what the alphas are. We worked out 1 over alpha A. That sum over the divisors is a product over the primes, 1 over alpha. And then when you work out what that is, it's 1 minus
Wow.
2 over P,
this is so strange.
which is like Mertens squared.
So I actually,
Sorry?
I'm getting hung up on trying to remember the consonants, because the two might come from like parity, so it might be e to the gamma.
I think it's actually 2e to the gamma in my memory. There's a 2 there in my
Yeah.
memory. I'll put a link to it. Yeah.
The philosophical consequences are bothering.
Yeah. Well, let me read that again.
Yeah.
So something that I really like about this too is that, like, if you go back and analyze what the lambdas end up giving you as set weights, it's basically like smooth truncations of Mobius. in
Yes.
one scale. So like if you go back and calculate, like we can calculate in terms of Y's, right?
Yes.
But then if you go back and see what your choice was in the lambdas.
So again, the YA eventually was right here. The YA is Mobius over alpha A, right? Mobius of A over A times alpha of A.
And then like go back through the analysis and see.
That means lambda of N is Mobius of N some.
Those are the constituents.
Yeah,
Like, you want to write lambdas as like a combination of,
right. It's not the lambdas, it's the
so like sum of lambda squared is equal to like a divisor sum of theta. and
Right.
Theta is the simple.
right.
So theta is going to be the smooth truncation.
Yeah, I'm already out of town, so out of time. So let me not do it. But yes, you can go back into this and I'll just put dot, dot, dot.
So it's kind of cool that like you start out with this arbitrary thing, and then it ends up being like it kind of captures the Mobius in the process of optimizing.
Right, so it's like, it's in the optimal, and then we need to take the optimal choice?
I mean, we want to get it as close an upper bound. And in fact, in practice, what you'll get as an upper bound that's off by a factor of 2 or something from the actual conjectured. If you instead of just getting crude upper bounds of some order, you can, if you want to look at the Hardy-Littlewood K-tuple conjecture, the Selberg lambda squared sieve gives you upper bounds of exactly, like there's a conjectured singular series, which is this product over primes. How many solutions are there in each prime? What the probability is of solving it in each prime. That's what I'm calling a delic. It's a product over all primes and the prime at infinity, which would be like x over log to the k x if you have a k tuple of numbers that you're trying to make prime. And the Selberg upper bound will give you that constant times x over log to the kx with an extra factor of 2. So the upper bound is really tight.
To make this work.
Is it 2 to the k?
Something.
It's like a 2 for each.
Or, I don't know,
I think it's better than,
because isn't it like a k-dimensional set?
yes, but it is a k-dimensional sieve. And if you do this by, if you get the upper bound by sieve, by Brun, Buchstab, combinatorial sieve, you'll get a much worse constant. So Selberg is easier and gives a better constant, but works on upper bounds. But there's ways to make it work on lower bounds too, but then the constants get worse. There's a whole.
Okay, so yeah, I'm wrong. That's.